Welcome, everybody. Glad you made it. My name is Jeff Kukert. I work for Copeland. Been with Copeland for a little over a year and a half, right in there. So I'll tell you a little bit about myself real quick, then I'll tell you a little bit about Copeland quick, and then we'll get into things. I've been in the industry, in the HVAC refrigeration industry for a little over 30 years. I did a lot of service for many of those years. Before I worked for Copeland, I taught at a college I was in my 14th year when I came to Copeland. So, been doing this for a while, but still learning every day. It's great stuff. Just being in this industry is a lot of fun. So at Copeland, as of last May, June area, we separated out of Emerson. If you guys did not know that, we have. So everything is Copeland branded now. So Copeland as a company, we're a $5.1 billion company. 80%, a little bit more than that, of our revenue comes from repair and replacement. So we're global. We're all over the place. We have around 30,000 patents and patents pending and stuff like that. So, with our umbrella, so we have Copeland compressors. Obviously, that's what we're going to talk about today. We also have Vilter under our umbrella. And then in the cold chain product, we have our rack controllers, E2, E3 controllers, Dixel, Proact, different controls and monitoring devices. And then we get into the comfort control with Verdant, Sensi, White Rogers, and then Elco. So those are all of our our brands under the Copeland name. So we're going to talk about scrolls and things to check and things to prevent them from overheating. So we're going to talk about how they work a little bit, the best practices, what we can do with compression ratios, and quickly come up with compression ratios to see if it's overheating. Talk about what we can do in low temperature applications to get our compressors cooler, and get into some troubleshooting stuff and how to use our apps to help you troubleshoot, which is how we're directing people a lot to help troubleshoot systems. And then identifying causes of compressor failures. So we don't have a whole lot of time. I'm used to training for a day or 3 days or 5 days. So 50 minutes is really quick. So we're going to shorten things up here. But I welcome if anybody has questions later and they see me wandering around, just come say hi. So, all right. So with our scroll compressors, on the top, this where the yellow line is, and then the entire top, that is our muffler plate. So above that, that's all discharge pressure. Okay? Below that is the low pressure. On the left here, you can see the little copper tube. That's an IPR. We'll talk about that in a second. We also have a TOD. This is the tube directing that onto our motor protector. And I'll get a little bit more into this in a second. With our scroll compressors, obviously, what makes it work is the scrolls themselves. In a second here, I will show another picture of a refrigeration scroll. So the inside looks a little different in a refrigeration scroll, and the flanks are a little wider. Okay? We were talking about CO2 earlier. Those scrolls look a little different even from these. So they're a little thicker and whatever. But on the scroll, on the piece on the left side is the orbiting scroll. Okay? And that's on the bottom. And the other one is the fixed scroll. So it's upside down right now. And all that does is it's bolted down. There's little sleeve guides that hold it down. And if it needs to, it will lift up 1 millimeter. So it's just a little bit of give. Okay. This Oldham coupling, the Oldham coupling fits into these little guides right here. And it takes our rotating motion. So our scroll compressors run at 3,500 RPM. And we take that rotating motion into an orbiting motion, okay? And there's always lubrication that's happening in between these two surfaces. Otherwise, we get problems. So our Oldham coupling is just a light aluminum piece. So there's not much to it. When you see the scroll work, when it's moving, it takes about 3 rotations for that gas to go from the low pressure side on the left side, on the top, to the center where it discharges out. So it brings it on the outside, and it's constantly doing it as it's, as we have it on the bringing gas in, we're discharging it. We got it in the medium pressure cell, we have gas in the high pressure. It's continually squeezing that refrigerant through. Our scroll compressors have compliance, so the axial lifts it up that 1 millimeter, and then we have the radial, so if we have any little droplets of liquid or debris, like that little red dot there, the actual, usually centrifugal force is what's keeping our scrolls together. It will separate a little bit. So it'll go lift up axially and radially, and that stuff will just go right through. Our floating seal, and I'll show you where this goes in a second here, but it's kind of like a donut, a flat donut. It's aluminum on one side, cast iron on the other. But you can see the little ridge right here. That ridge goes up against that muffler plate. And when it's pushed up, it separates the 2 pressures. So we have high pressure on top and the low pressure on the bottom. When our compressor shuts off, that goes down, and now the pressures equalize inside of our compressor. Okay? And that's on the picture on the left there is what it looks like on the fixed scroll. So it's pushed in there. So if you ever take apart a scroll compressor, you can pull those out. You just need like a little pick or little screwdrivers, and it will come out of there. Okay, and this picture has it's kind of a cutaway. So again, you can see our muffler plate. This part right here, that would be our floating seal. And you can see the little hole. So when our compressor's off, and when it starts to get the compression process going, it lifts that floating seal up, and then it seals against that muffler plate there. Then when it turns off, the floating seal goes down on those little ridges there. So in this picture, you can see the little sleeve guides for that fixed scroll to lift up that 1 millimeter. In that little circle is our check valve. Other different compressors have check valves in different spots also to prevent when we have a larger compressor with a lot of capacity and discharge gas. We don't want that high pressure go into the low pressure and turn our scroll set the wrong way. So this is a little picture of how it works. And if you guys didn't know, we even put little arrows so the refrigerant knows where to go. So you guys probably didn't know that, did you? So on the left, so our bottom bearing should always have oil. It should be in oil in there. And I'll show in a second what that crankshaft and everything looks like. But it brings oil with centrifugal force to the top to lubricate all the parts and pieces inside that compressor. Okay? The only scroll compressor that we use an actual pump for the oil would be a positive displacement pump, would be for the variable speed. Yes?
Inside of the bottom of the shaft, I believe there are 2 little feet that scoop the oil up.
Exactly. Yep, and I'll show a little picture of that. The little flingers. Yeah, you should be up here teaching. That's awesome. So, a lower bearing, main bearing, and then drive bearing with this straddle on top. Okay? So all those surfaces need to be lubricated inside the compressor at all times. Again, anytime we have metal on metal, we need to lubricate that, right? And we need to keep that temperature down. Otherwise, we're going to lose our lubrication process. So there's the little flingers that you were just talking about, right on the bottom. Those do pull right out if you wanted to. And you can kind of see the crankshaft, how it's off-centered. And when it rotates at 3,500 RPM with centrifugal force, it's pulling that oil right up. And it's going through the little journals, lubricating the parts wherever we need. As far as protection for our compressors, we have a lot of protection built in. So we have the floating seal is actually a protection device if the compression ratio gets too high. The TOD goes off of temperature, okay? Just a bimetal disc, if you think of like a high temperature sensor for a furnace. And it trips, the bimetal flexes, and it usually opens a switch. Well, in this case, when it flexes, the refrigerant flows through it, okay? So there's no switches or anything, it just flows the refrigerant through it. And then the IPR goes off of pressure differential from the high side to the low side, okay? And both of those, the TOD and the IPR, will direct that high pressure right on top of that motor protector. So the motor protector will go off on temperature or higher current. So this shows that floating seal. Now, I'll talk about compression ratio in a second here, but once we hit in air conditioning, for an air conditioning scroll, over 11:1 compression ratio, that floating seal will go off balance, and then we'll not be able to compress with that compressor anymore. And with the refrigeration side, once we hit 26:1, then it's going to go off balance, okay? All right, so now a little test. You guys are going to have to answer these questions. So A is actually the thing, this thing, the blue thing. What is that called? Muffler plate. You guys remember that? Yep. And then B is the little donut-shaped thing. What is that called? Floating seal. Floating seal. C is the top scroll. What's that called? Fixed scroll. Yep. And then D would be the bottom. What's that one called? Orbiting, or yep. And then E is the thing that takes the rotating motion. Oldham coupling, yep, into an orbiting motion. F is what is rotating in there. The crankshaft, yep, and bringing the oil up. And then G is on the bottom part of that compressor. What is that? Thing that makes it move. That's our motor. So it could be our stator, rotor. Yep, absolutely. Good job. You guys didn't know I was going to quiz you right away, did you? So here's a picture of the refrigeration scroll. You see how the lobes are at the end is different than the other one? And then it's a little wider. So I just wanted to put that picture in there because if people have not taken compressors apart, which I highly recommend, if you have a problem with a compressor, whatever kind of compressor it is, if it's out of warranty, take it apart. Find out what happened so the next one doesn't go bad. If it's in warranty, see if it has to go back first, okay? And it depends on what kind of compressor it is, but. All right, so best practices. So a lot of stuff that we'll be going through this next few days will be about best practices and things like that. But when people don't use the best practices on our systems and they're not installing them correctly, our compressors fail, right? So we have to be careful when we're brazing lines together. We have to purge with nitrogen. So nitrogen is an inert gas, so it displaces the air. So for example, if this room were full of nitrogen, it would be kind of hard to breathe, right? Because I need oxygen to breathe. I don't know about you guys. So we would have no oxygen. So if we have a pipe with nitrogen flowing through it, there's no oxygen to burn in there. We're not going to get the oxidation inside, right? So that's very, very important not to plug up all of our different parts inside of our system. So again, you can see on the left with the oxidation when we're, and you guys probably already know this, but when on the right, without oxidation, it's almost going to look like new or better than it does on the outside, right? So very, very important. And it's always been important, but now that we're starting to use these newer refrigerants, A2Ls, A3s, CO2, whatever, refrigerants that we haven't used in the past, it's going to be a lot more important, right? We have to make sure that we have no leaks in our system, right? So first we're going to braze all the pipes together, then we're going to make sure we have no leaks, right? And then what comes next in the system? What do we need to do before we put refrigerant in it? Evacuate the system, yep. So we evacuate that system. Whatever the OEM says we need to evacuate it to, usually they say 500 microns, but sometimes we need to go lower than that, right? So make sure we're doing a really good job of evacuating the system. And believe me, when you take apart compressors and the system has not been evacuated properly, you can tell. And I have taken apart a lot of compressors, and you can see we have copper plating all over the place, and that's because somebody didn't take the time to make sure they evacuated the system properly, right? Just put a couple of little fun facts on the right side here. I know for years when I used to evacuate systems, I always used my manifold gauge set just because that's how I was taught, right? And now that I've figured things out a little bit more as we learn, right? We're continually learning in our industry new ways of doing things better and saving time. Through that 1/4-inch hose with valve cores in there, even if I was using a 6 CFM vacuum pump, I was only getting 0.2 CFM through my hoses, right? So once you start pulling those valve cores out, putting bigger hoses on, you're going to be able to evacuate that system a lot quicker, right? The other thing I wanted to point out with our compressors, our scroll compressors, it's a copper clad. So if you overheat it, that cladding will go away. So you have to use a higher silver content brazing material to connect your pipe into, because it'll be steel then, right? So there won't be any. So be careful whenever you're brazing. Do not heat up fittings to disconnect them. Always cut them out, whatever it is in the system. With crankcase heaters, and I just threw this in there just as a little added thing, but where the crankcase heaters go we have a vertical weld in our scroll compressor, and right where they connect here, where you bolt it down to tighten it, this doesn't go real tight against the compressor. So if you put that vertical welded seam right there, it fits a lot better around that compressor, right? And you can look on whatever, if you're using our apps, you can go right to the AE bulletins, our application engineering bulletins, and it will tell you exactly what the height that you need to be, where you want to put that crankcase heater. Okay? And then with the molded plugs, never pull that molded plug out when the compressor is right in front of you facing the compressor. All right? If there's gas in there, I was doing a training somewhere, and somebody was telling me they were watching some OEM do this live video, and the person was right in front of the unit and pulled off that plug, and there was refrigerant in the system, and the pin in the fusite let go. And the pin hit the guy, and refrigerant went flying all over the place. So don't do that. That's very dangerous. So always stand to the side when you're pulling that plug out. So it's something that people don't really think about, but be careful. All right, now we're going to get into compression ratio. So we're going to make this really easy. All we have to do is take our discharge pressure and our suction pressure. We're going to add 15, 14.7. For easy math, we're going to say 15. Okay? And then we're going to divide those. So whatever you have, you're going to take the high side divided by the low side, and it'll come up with a number. And we came up with these numbers. I don't know who somebody came up with these numbers for us. But when we talk about high temp, again, we're talking about air conditioning or high temp refrigeration. We want a compression ratio around 3 to 1. Okay? It's always whatever that number is going to be, it's going to be to 1. Okay? Medium temp refrigeration is going to be 5 to 1. Okay? And then low temp will be 10 to 1. So you guys remember back that floating seal for refrigeration, when did that go off balance for the low temp? It was 26, really high, yeah. So believe me, if that's going off balance, you're going to have other problems in that system also. You're going to know that there's a problem. So that's kind of like a last resort type thing. Anybody not seen one of our compressor performance sheets before? So back in the day, we used to get these blue books that Copeland would make, and then somebody would put the sheets from all these compressors in there. Now today, all this stuff is on your app, and it's a lot easier. So I'm sure you guys can all read these numbers back there, right? Yeah. But the thing to remember is you need to know, obviously, the model number of that compressor, right? You need to know what refrigerant is in there, and then what the application is, and the voltage, but when you go in there. And it talks about going in through with the model number here. This example, as you guys probably can't read that, is a ZS15 and then K. K is the multiplier, and 15 is the capacity. So as an example, I'm going to blow this up a little bit. So using AHRI guidelines for what they test medium temp units for, at 20 degree evaporator temp and 120 degree condensing temp, we're going to see what the BTUs is of this compressor. Okay, so as an example, if you look at the numbers, so we go to 20, and the numbers in parentheses, that's the actual pressure. Okay, so if you went to your gauges, it would say 55 psig. Okay, now we go to the high side, 120, and our gauges would say 310 psig, right? So we bring those together, and we get 15,300 BTUs. Does that look familiar? Look at our model number. That's what we get. Now, as the conditions change, do we always get the same amount of BTUs out of it? No. And in the refrigeration world, or in the air conditioning world, how often are our conditions the same? Never, right? So everything is always going to change. So when you look at a system, in this example, if you look way on the bottom of the page, it shows what all those letters mean. But the C is the capacity, P is power in watts, A is the amps. So as an example, amps on this one is 7.3. If we start changing things, our amp draw is going to change, right? So that's why we want to bring people to our apps. You can put your information in, and it'll show you at those conditions, this is what your amp draw should be. For low temperature applications, we need to, because remember, when we're dealing with lower suction pressure, our discharge temperature, everything is running hotter. Our mass flow is lower, so we're not bringing as much refrigerant through the system. So we had to do something, and we came up with injection. So in the refrigeration world, we've used liquid injection for years. Okay? So we inject refrigerant into that scroll set in the mid-range of that scroll set, and it instantly cools down that compressor. And I'll show you a little diagram with a pressure enthalpy diagram, kind of how that works. But so we have liquid injection, we have vapor injection, which we have a couple more components in that part, and wet injection gets a little bit more involved when we talk about more things. It's a lot more computerized and different things. So with injection, all we're doing is we have our normal system. We have our compressor going to our condenser, going to our metering device, to our evaporator, back to our compressor, right? Now for injection, we're just going off the liquid line here, and we're going through a solenoid, because anytime that compressor's off, we don't want that refrigerant to migrate into our compressor, right? And then, so whenever we need this, the system's on, that's going to be open, and then we have a metering device, okay? And that's bringing the refrigerant into our scroll set. And that little red pinkish line right there shows where it's bringing it into that scroll set to cool it down, okay? This is kind of what it looks like. So it's the DTC valve. So on the left side, you can see mounted right here. There's a temperature probe right here that goes right on the top of the compressor, okay? And then this valve is almost like an expansion valve. You can see the little pins inside. So there's some drawings of it, or pictures of it taken apart. And it reacts with temperature, okay? So as that discharge temperature goes up, it opens up more. Okay, does that make sense? The larger compressors, instead of using a manual valve like that, uses an electronic valve. Okay, so we got a little stepper valve over there. This is showing another way. This happens to be a vapor injection, but this little spot right here goes into that tube, and then it brings that tube into our scroll set and to cool it down. And this just shows the little ports inside that scroll set to cool down that compressor, okay? So this is a pressure enthalpy diagram. So with vapor injection, the thing we're adding here is a heat exchanger, okay? So we have an extra load that we're adding, But with this vapor injection system, we get 50% more capacity and 20% more efficiency. Okay, so ultimately, now I can use a smaller compressor, okay, because it's so much more efficient. And with this heat exchanger, I'm subcooling that liquid going into my expansion valve, okay? So when we look over here, we have our compression cycle follows the lines of entropy on our pressure enthalpy diagram. And normally on a system, if we're starting off right here for temperature, our discharge would follow that line of entropy, and our temperature would be way over here, and it'd be very hot, right? When we have injection, we are injecting into the middle of that scroll set. All of a sudden, look at our temperature go down instantly. Now we have a lower temperature. So pressure enthalpy diagram, we were just looking at a snapshot of that system, right? So we can really see it when we look at a pressure enthalpy diagram, how that cools down that compressor with injection. All right, so with our apps. So how many people in here use any of our Copeland apps? A lot of you, great, that's awesome. You would, every week I'm somewhere else pretty much training, and there's some classes that I'll do and nobody's ever used our apps. So it's really crazy to me because we make these apps to help people out in the industry, right? To make their job quicker and to solve problems, a lot faster and not to have misdiagnosis out there, right? So you can also get Copeland Mobile not only on your phone, but on desktop. Okay, so I took some pictures from the desktop version. That's what I'm going to go over in a second here. So if somebody's used to working on computers all the time, it might be easier just to do it on the desktop version. So if you just Google whatever, Copeland Mobile desktop version, you'll get to this page. Then you'll see with your credentials, it'll show you your last, 10 searches that you've looked at, okay? So in my example, I picked a ZF24 kVE compressor, okay? So we have to pick out whatever application we're dealing with, what the refrigerant is. So we have 404A, 507. That's pretty much it with this one. Some compressors will have a lot of different refrigerants in there. And then the different voltages. When you're looking at the app, you can see on the left side here, I'm going to go to performance in a second. That's where you can actually see that performance chart that we were just looking at. But when you go into if you just want troubleshooting information, there's just questions. When you go to the troubleshooting one, you just start answering questions. And then at the end, it'll tell you, do not replace the compressor if you don't have to replace the compressor, right? The diagnostics is a really cool thing. If anybody has not used that, you actually put your pressures, your amp draw, your voltage in there, and it will tell you how far off you are with those parameters from what it should be. And then there'll be a button that says troubleshoot, and you push that button and it'll tell you exactly the steps to go through to look for things, okay? So we try to make it as easy as possible for everybody out there. But we're going to go to performance right now. So in the performance, it'll look like this. The rated performance looks just like that almost. I think I'll show it in the next one. Dynamic performance is what you actually see in that system, and you can put your information in. The full performance, the PDF, that's what we were just looking at, okay? And then the operating envelope is what we want that compressor for long life to be running in that operating envelope at all times, right? So in this example, the rated performance, we have a couple different rated performances, but we're going to concentrate on the left side there. So we have an evap temp of -25 and a condensing temp of 105, right? So in here, you can also look our amp draw at this, what it's running at right now, would be 21 amps. That's what we want to see. If we clicked the PDF version, this is what it looked like. If you're on your phone, these all have the little share symbol, and you know, a lot of times I'll text it to people or I'll email it to myself if I want to remember it later, or document it or take a picture of it or whatever. So if there's information, you know, there's so much great information in this app. But at those you know, rated performance, this is where, so we're at -25 and 105. So that's where that dot is where it's running right now. Okay? So now I'm going to change what it's running at. So I just went to the dynamic performance, and I changed it to a -30 degrees and a condensing temperature of 115. Okay? So just so we can see all the other information I just kept the same as now, and I just hit calculate. And now it shows my BTUs now is 28,800. So our BTUs went down, right? And then our amp draw is 22 amps that we're looking at in this application. So every time you're at a system, those amp draws are going to be different. So you can't just look at a nameplate or something like that because it's a rated load amps. But then when we look at the actual operating envelope, now we're over more. So if my little dot were outside of that, then we'd have a problem. Usually our safeties would kick in, right? So we're just further over. It'll still work. It's just not, anything that happens to our system pretty much, we are going to lose efficiency and we're going to lose capacity, right? And nowadays, we just can't afford to lose those things. Back in, you know, 80s, 90s, whatever, people didn't care about all that stuff with how much power we had. Everything was oversized, so if we didn't get quite the right charge in there, didn't matter, right? Now everything's made with tighter tolerances, and it does matter nowadays. All right, getting into compressor failures. So when we get compressors back under warranty, 80% of them, on the tag, it'll say an electrical problem. But when we tear them apart, actually 80% of it is a mechanical failure that caused the electrical failure. Okay? So the people that take apart our compressors are really good at what they do. I'll say that. And they can do chemical, you know, breakdowns of everything and find out what's inside that system. Okay? So the root cause is what we're concerned about. So when you take apart a compressor, you can actually see what's going on in that system. What do I need to fix, right? So these are all the different common causes of failure. But today we're just concentrating on the overheating part. So when we have a high compression ratio, that compressor is going to be overheating. So without even taking out our thermometer, we have our pressures. We just add 15 and divide those. We're going to come up with the number, right? And it takes, you know, less than a minute to figure that out. And without that temperature probe, you're going to know if that compressor is overworking, if there's a system problem somewhere. You're going to have to be looking somewhere. High return gas temperatures. Say we have a unit on the roof, and we're in Phoenix, Arizona. We have a nice black roof and with no insulation on that suction line. What do you think is going to happen to that suction line? Do you think it's going to gain a little bit of heat? Absolutely it is. So that heat is going to affect that system. So once we get to about 300, 320, our oil starts to lose lubricity. Now that's just a fun word to say, so I like to put that in all my little trainings, lubricity. Say that at home, you know, 300 to 320 degrees. So we need that oil to be doing its job, right? That lubricant to be lubricating our parts. Once we get to 350, then our oil will start to break down. Now I've taken apart compressors where there's no oil and it's just a powder. Now imagine what happened to that thing, right? So it's amazing. I've seen so many goofy things inside of compressors that shouldn't be there, but it is. That's what happens. So when we take apart a scroll compressor and you see color, like dark colors like that, that's from high heat temperatures, right? So that's our muffler plate. It's a temperature probe from a DTC valve right there, our IPR. Here's a scroll set with bluing in there. Now this is not something you can say, hey Copeland, I want one of those cool blue scroll sets. This has to be earned, right? That just doesn't happen. So if we take apart a compressor and it looks like that, we know that it has been overheated, right?
How long does that take? Depends on temperature.
Generally, yeah, it depends on the temperature, but a lot of times with overheating, it happens over a long period of time. So
10 years old.
not necessarily. I've seen it 6 months old. So, but it might be a system that runs constantly. But yeah, but if it's constantly overheated for 6 months, it'll do that. If you remember what our floating seal looked like before, if you see one that looks like this, that is not good. You can see, it's a little hard to see it in here, but this is what's supposed to be green, but you can see it's ripped here. This has come off balance, this floating seal. So that pressure differential in that system has gone too far. So obviously you can see it's had a lot of problems. So things we have to look out for, always on whatever system you're working on, air conditioning or refrigeration, always think of keeping that suction pressure up. So we want that suction pressure to be as high as possible to maintain whatever temperature we want in our medium, right? So in this case, so when we look at, this will just equal compression ratio, but on the high side, if we have a dirty or blocked condenser, we have to make sure that's clean. Then how do we know if a condenser is clean? I would say if you're the one that cleaned it and you know for sure. Because I personally have gone to units, I have some pictures that I do put in some other trainings, that person said, I cleaned every one of those units up on the roof. So the problem's not that. And I go up there, and this happened to be a very large rooftop, and it had a split condenser. So they cleaned it, but they did not split, because I could see they obviously did not hit, they had very old zip ties in the condenser holding it together. So you pull apart the condenser, and it looked like a blanket inside. That was not clean, right? Somebody said it was clean, but I didn't believe them. Or if you look at a lot of mini splits, a lot of those will have 2 or 3 pass condenser coils. You have to split those apart. So make sure everything is clean in there. Recirculation of condenser air. So have we seen that before, where people like to put their shrubbery around the condensing unit or put a deck or porch? Yeah, you name it. I think it should be in the center of the yard, right? They're beautiful, right? So condenser fan operation. We get these kind of one-size-fits-all condenser fans, and you can rotate the speed, so you can change the wiring, which direction. So who knows if somebody put the fan blade on the right direction anyway, or if it's going in the right direction. So you have to be paying attention with all that. If the system's overcharged, or we have non-condensables in the system, then we get to the low side. If we have the wrong components, metering device issues, that could cause a problem, right? Loss of refrigerant. So if we're low on refrigerant, plug filter dryers and strainers in our system. So we have to be looking out for all this stuff. Suction line pressure drop. All different things that will cause low suction pressure. And again, the lower the suction pressure, that's going to affect our compression ratio more than the higher discharge pressure. Okay? So if we just talk air conditioning for a sec, if somebody has a plugged filter and their temperature is lower in their evaporator, that's going to cost them more money than if their condenser was plugged up. We always want to check our temperature 6 inches away from our compressor, and it should be no higher than 225 degrees. Okay? So 225 to stay alive. Just remember that, 225 to stay alive. If it's 225 there, it's 50 to 75 degrees warmer inside of our compressor. And what temperature does the oil start breaking down at? Yeah, it kind of sounds familiar, right? All right, so there's so many different things that we can check in our system. If we have 2 to 3 degree temperature difference in our filter dryer, we probably have a problem, right? We want to make sure we have subcooled liquid going to our metering device, right? We can check our temperatures, our pressures, our superheat. We can check our amps, our compressor superheat, our discharge, our compression ratio. We can make sure that our condenser's clean, we have good subcooling. So many different things to check on our system before we start adjusting things. We have to make sure everything's working correctly, make sure we have the correct airflow. You know, no matter what type of system we're using, whether it's an air conditioning system where we can actually adjust the airflow, which most, you know, I would say many systems out there are not set to the proper airflow in the first place. So if we're not setting that stuff in the beginning, we're going to have a problem, right? In the refrigeration side, it's usually that's a one speed is fixed except for if it's dirty. Or now in the refrigeration world, we have, if you guys have seen the ECM motors that you can program, the RPMs, and you can make it turn different directions. So it's really awesome because you don't have to carry as many motors, but what if somebody programs it to the wrong speed or makes it go the wrong direction? So you got to be looking out for all those things. Highly recommend using some sort of a troubleshooting chart. So when you have a system in the first time, when you're getting it going, commissioning that system, get all those details down, right? And then if you're having problems, compare it. I was doing a training not that long ago in North Carolina, and one of the young man that worked at a company, he's been there for 10 years, and he said his company has always used software, but it has the same information. So they put, every time they're at a job site, they put all this information down, and then 10 years later, you can still see everybody's, whatever they've done to that system, and what at that day, at those temperatures, what that system was doing. And that really helps, right? But sometimes we like to overthink things, and a lot of times problems are basic. So if we go back to the basics, we're going to be able to figure out what problems are, right? We also have a troubleshooting chart that will help you, you know, kind of, it's not real formal, but it will kind of get you to the right spot sometimes. This is in one of our technical manuals. And then lastly, I was just going to show you a couple pictures. So this spring, I don't remember, June maybe, I was in our factory where they do teardowns of warranty scroll compressors. And so they're showing me these compressors that come through. They go through a device that looks similar to this, and it's like a big can opener. A big wheel, it cuts open. The compressor, then it keeps on going through. If the compressor had no problems, it goes to, this is in a different room. So this is a compressor that had no problems, okay? Almost 40% of our compressors that get sent back under warranty, there's nothing wrong with them.
Wow, is that high, 40%?
Yeah, so it's crazy. So in this one, we just use a bandsaw, it turns it on those wheels, and then they cut it off, and then it goes into this machine, and they push a button, and it rips a strip in the back of the compressor, and then they push another button, and then the stator comes out of that compressor. And they want to look at the stator of that compressor and just make sure we didn't do anything wrong. And then it goes into a recycling bin. And I think I was there on a Wednesday morning, and the guy said, this is a big recycling bin. He said that recycling bin was empty on Monday. And this is just warranty compressors that go in this bin of just these parts. So it's crazy to me. But I took some other pictures. I took a lot of fun pictures. But this compressor in the middle here, are our tags normally tan? No, they're white. So if it's tan like that, you can see we had a problem, right? And that compressor was less than 6 months old. So the one on the left there, that compressor on the left on the top was very interesting. That compressor was the second replacement compressor, and that system was less than 6 months old. And it got that dirty in less than 6 months. Isn't that crazy? But everybody see that little orange stuff on the top? Anybody guess what that is? Something that shouldn't be inside, it should not be inside of our system at all. We don't use it for anything except for sealing things. It's RTV silicone. And that took a while. We had to analyze it and figure it out. Because at first we thought it was part of where the plug is for the compressor, the fusite, but because that was blown also, but that was not the material in there. That had a broken scroll set. It had a lot of problems, but yeah. But very interesting. So here you can see when we don't have lubrication. So if it overheats or we get refrigerant, getting rid of that oil, we get galling. So we get that orbiting process, and it creates little circles inside those surfaces. All right. Thank you. And if anybody needs anything, feel free, Copeland.com. Yeah, you have a question?
Look here, Playboy.
If I understand economics at all, what you're telling us is that because of the 40% of the compressors that are sent back previously, and you need to raise the price of your product by 40%.
That's why they hire me to lower that number. Yeah.
You're having to raise prices from people that actually do the job.
Yeah. So we want to make sure everybody's aware, and that's why we made all these apps, why we make our electronic devices, to help people out in the field so they don't misdiagnose problems. Yeah, it's crazy. Oh, I'm sorry.
That one with all the crap in it,
Yes.
is that a new home system, or did they just put a new condenser unit on the old system?
That was a new system. Whole thing was new, and that was the second compressor in that new system.
So how does all that crap get in there?
No idea. Yeah, your guess is as good as mine.
Long install,
Yeah, who knows? I don't know the specifics on that one, but yeah, all I know is yeah. I have no idea. It's crazy. Did you have a question?
Is there a chargeback rate for compressors that are returned that are not?
Well, what I would say for as far as warranty compressors, a lot of times we're pretty lenient on the first time, but we keep track of all the information, so we know if somebody sends in another compressor and has the same problem, we will probably deny warranty the next time. Yeah, we have a big denied sticker stamp, and believe me, that guy likes to go denied. So you better have a good reason. Yeah, but we'll take apart compressors. I encourage people, but we also will, if you had a compressor under warranty and you wanted to find out what was going on, you didn't want to cut it open yourself, and you wanted to have us analyze it, we would do that. So I don't remember what the charge is. I don't get into the dollars part of it, everything, but that we would do. So yeah. Any more questions? Awesome. Thanks, everybody.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community, for techs, by techs.